All right, here we're going to take a look now at example 3. For what values of x does this series converge? Now again, I'm going to go ahead and kind of like what I did up above, I'm going to think about what polynomial I actually kind of have here shaping up. So let's see what happens when I start by plugging in the number 1. If I plugged in 1 for n, I'm going to get an x minus a 3. If I plugged in a 2, I'm going to get like a half x minus a 3 squared. And then maybe like a third x minus a 3 to the third. And this goes on forever. That's like an easy polynomial sort of thing, except that it goes on for all eternity. And I might be able to guess right away, can you think of a value that I could plug in for x that would definitely allow me to add up everything really easily? Well, you might have been able to guess that 3 is a perfectly good value because that's going to make this 0 plus 0 plus 0 all the way down the line. Okay, so we want to go ahead though and figure out all the values that could work here. And so again, we'll use the ratio test. I would ask you to try to go ahead and use the ratio test right now. Pause the video and see how far you can get. You can kind of simulate what we did in the example that's up above. Okay, I'm going to go ahead and show how I would use the ratio test here. And I'll start just by saying we will use the ratio test. All right, so let's see. I'm going to compute the limit as n approaches infinity. I'm going to set this up, put my absolute value bars down. So I'm going to have x minus 3 to the power of n plus 1 over n plus 1. In the denominator, x minus 3 to the n over n. Again, I have to get rid of the absolute value bars before I can do anything else. And in order to do that, I can start to think carefully about what I actually have here. The n plus 1, the bottom of that top fraction, that's definitely not ever going to be negative. It is possible that x minus 3 could be negative, right? Like what if I plugged in 0 for x? Then definitely I get a negative there. And then based on what n is, I might get a negative result. So just like we did up above, I could guarantee that this will be positive by just first guaranteeing that I absolute value that x minus 3. If I do that, then when I raise it to a power, there's no way I could come up with a negative result. I'll do the same thing down here. I'll just absolute value that bit, and now I'm good to go. I'll then multiply by the reciprocal to make this a little bit easier to evaluate the limit on. You'll see that I'm going to get an x minus a 3 to power n plus 1 times an n over an n plus 1 times an absolute value of an x minus 3 all to power n. Now, of course, I can simplify this up a little bit. I'm going to write it in the following way. I can see that I have a lot of similar common absolute values top and bottom. And it looks like at the end of the day, I'm just going to be left with one of them. And it's in the numerator. The rest of the stuff, I'm going to kind of write over here in its own fraction. Again, when I think about this limit, what I'm going to end up with is a limit here that has only n moving, which means that once I've picked a value of x, this absolute value stuff here is completely constant. And if it's constant, I'm more than free to pull it outside of that limit. Again, I'm interested in figuring out what this limit is going to be equal to. Remember, that's going to be my value rho. So here you might be able to guess really quickly. Yeah, the limit there is going to be 1, which means that the limit that I end up with, the value for rho for the ratio test, is absolute value of x minus 3. Okay, so remember with the ratio test, what I'm always trying to determine is if the result of my limit was greater than 1, smaller than 1, or equal to 1. So here's the question. Is the absolute value of x minus 3 greater than 1, smaller than 1, or equal to 1? Well, I guess that kind of really depends. If I plug in 0, then it's definitely greater than 1. If I plug in something like 2.5, I'm going to get something less than 1. And if I plug in something like a 4, I can get exactly 1. I can get like all of those results. So I might write something like this. In order for the series to converge, we need the absolute value of x minus 3 to be less than 1. That's what we would need, right? We want that result to be less than 1 to get convergent. So the question is, what values of x can make that happen? So I need to solve that inequality. So I'll even write that here. We solve this inequality. I have to think carefully about how this inequality would be solved, but I should be able to deduce with some basic algebra that this means that x minus 3 should be wedged between -1 and +1. That, of course, implies that if I added 3 to everything, x would have to be wedged between 2 and 4. So I think if I plug in any number between 2 and 4, I will get a convergent result. Okay, so we could even test our theory there. Remember at the beginning, we said that if we plugged in 3, we would definitely get something that's converging. It would get 0. And notice 3 is one of the values that we have here. Okay, so this is great news. We kind of have found a whole bunch of really good values here where the series converges. The series converges when x, or I'll say 4x, between 4 and 2, right? That's awesome. But we have a slight problem. Again, if I was to go ahead and think back to what the ratio test said, what would the ratio test tell me would happen if my limit here ever equaled 1 as a total? Yeah, it would say inconclusive, right? So, that's a big problem. If the ratio test can tell me inconclusive, then there should be some numbers here that the ratio test hasn't told me anything about. Notice, what are the values that I could plug in for x that would cause this absolute value to turn into 1? Note, there are 2 of these values. Well, one of the values here would definitely be 4. The other value could be 2. And it is no surprise those are the endpoints of this interval. It'll always be those endpoints. So we're going to have to check those endpoints separately. So we'll check the endpoints separately. Again, I'm doing this because I know that the ratio test fails there. So I'll just have to say, what would happen if, say, x was a 2? Well, if x was a 2, then let me go all the way back to my original series and say I have. If x was the number 2 here, then notice I would have -1 to the power of n. Now I'm going to write this here. Oh boy, I'm almost out of space. I'm going to write this here like this and summarize this in a few steps. I would get something like this. And the question would be, does that addition problem converge or diverge? Which means now I have to go all the way back to chapter 5 and I have to recall all the information and ideas and tests that I have there. But wait, this one's actually super simple. This is a special kind of series. What kind of series is it? Yeah, it's an alternating series. And actually I can see, what would the a sub n be in this alternating series? The part without the -1 to the power. Well, yeah, that would be just 1 over n. So is that a decreasing sequence? Of course. Does it have a limit that goes to 0? Of course. So I know that this converges by the alternating series test. So I actually know that 2 is also a good value. I still have to check, though, what happens if x is equal to 4. If x is equal to 4, then notice my series becomes something like this. Again, I'm just plugging in 4 for wherever x occurred. Now, if I do this, in the top, I'm going to get 1 to the n, but that's always just 1. So I'm going to get 1 over n. And this, of course, diverges because it's the harmonic. So this value is not good. So as a total conclusion, I can write that the series converges for x is between 4 and 2, but notice I can be equal to the 2. Wow. So a problem like this can take a little bit of time. I have to understand ratio test, which we'll use pretty much every time, but also how to check those endpoints. Okay, this is super, super important. We've essentially again found here is that if this green thing up here is like a polynomial function, we've identified the domain. What are the x's we're allowed to plug into it? Okay, in the next video, it'll be the final video for this section, and we'll talk a little bit there about what are the possibilities for different kinds of domains that we could get for these power series, these new polynomial function things.